In this module, we will basically study the fundamentals of quantum mechanics. Our aim will be to know how quantum mechanics operates. So in this regard, first we will study about the basic equation of quantum mechanics. We know that there are two forms of this. We will know what are these two forms. One is time dependent and other is time independent. And after that, we will study what are the various steps which one follows while studying quantum mechanically a system. And lastly, we will also study how to write Schrodinger equation for a chemical system. So these will be the four major steps which we will be studying in this module. Now we have already studied in the previous module as to how quantum mechanics originated from the failure of classical mechanics. We have learned that classical mechanics could not very well explain the behavior of certain experimental phenomena and how it led to the origin of quantum mechanics. This has already been discussed. We now know that quantum mechanics is basically a theoretical science, a science which takes into account the dual behavior of microscopic matter. And what's this dual behavior? This dual behavior is particle character and wave character. Once it was established that microscopic matter has dual behavior, or in other words, this dual behavior is very significant in the case of microscopic matter, then it was thought how to formulate a science which could take into account this dual behavior of matter. In this regard, two approaches were followed. One was the approach of Schrodinger, and the second was the approach of Heisenberg. The approach of Schrodinger is what we call wave mechanics or Schrodinger's quantum mechanics, and the approach of Heisenberg is called matrix mechanics. This is so because its basic formulation is matrices, whereas in the case of Schrodinger, the basic formulation is partial differential equation. At the first sight, it looks as if the two approaches are different, but Dirac showed that in essence these two formalisms may be different, but in essence both are the same. In our course, we will be dealing with Schrodinger's quantum mechanics, which is based on partial differential equations. Now, if we have to study quantum mechanically any system using Schrodinger's quantum mechanics, how does one start? There is a fundamental equation of Schrodinger's quantum mechanics, and that is called Schrodinger equation. This equation is normally written in two forms. One is time dependent Schrodinger equation and the other is time independent Schrodinger equation. If we look at the time dependent Schrodinger equation, here one can see that on the left hand side we have H cap. H cap is Hamiltonian, or in other words, it is the total energy operator. In quantum mechanics, whenever we denote an operator, we denote it with the help of a cap, and then is psi, H cap psi. Psi is the wave function which defines the state of the system. And then on the right hand side we have iota H cross is H upon 2 pi and then del psi by del t. This is time dependent Schrodinger equation. But please remember that this equation is used only for non-conservative systems. That means those systems where energy changes with time. But in our course, what we will be studying here, we will be focusing on time independent Schrodinger equation, which is written as follows. Time independent Schrodinger equation, as you can see, is written in the form H cap psi is equal to E psi. Here H cap, as already mentioned, is the total energy operator, psi is the wave function, and E is the total energy of the system. Please remember, there is a difference between the total energy E of the system and H cap, which is the corresponding operator for the total energy. So this difference must be very well understood. So according to this time independent Schrodinger equation, as you can see, when H cap operates on psi, it gives E psi. Now it is operator which is operator. What is an operator? Operator is basically a function which operates on something which follows it. In this case, you can see that H cap or Hamiltonian is operating on psi, and when it operates on psi, it gives back psi along with E, which is the total energy of the system. Now one may ask as to what is this Hamiltonian operator, which is the total energy operator. Here I would like to mention that total energy of a system can be divided into two parts, kinetic energy and potential energy. So total energy operator Hamiltonian therefore is made up of two operators, T cap, which is the kinetic energy operator, and V cap, which is the potential energy operator. So this is something which one needs to keep it in mind. After having studied this, now the question comes, how does quantum mechanics approach? How does quantum mechanics in reality operate? If you want to study quantum mechanically a microscopic system, how will you start? So here I would like to mention that the operation of quantum mechanics basically involves 4 steps, and these 4 steps summarize the entire operation of quantum mechanics. The first step is always that whatsoever system you are studying, the first step is you write the Schrodinger equation for that system. Now Schrodinger equation, as we just now studied, is H cap psi is equal to E psi. Then the question comes, what does it mean when we say that we have to write Schrodinger equation? Writing Schrodinger equation means we will have to define Hamiltonian explicitly. We will have to define what is Hamiltonian. That means what is the kinetic energy operator and what is the potential energy operators. Once these two quantities are defined, then Hamiltonian is defined, and therefore Schrodinger equation stands written. Now I will discuss very briefly some of the examples. Let's take a very simple system, and suppose it is a system consisting of one particle of mass m, and suppose it is moving in one dimension, say along x direction, and further that suppose its potential energy is 0. Please remember, potential energy of a system can be 0, but kinetic energy cannot be 0. So here we are assuming a case of a particle in one dimensional box moving along x direction and having potential energy equal to 0. Now for such a system, what will be the corresponding Schrodinger equation? Let's see. Here Schrodinger equation will be, as you can see, potential energy is 0. So H cap psi equals E psi would mean T cap psi equals E psi, and T cap, which is the kinetic energy operator, in this case it is the kinetic energy operator in the x direction. So this will become equal to minus h square upon 8 pi square m d2 by dx2. This is the expression for the kinetic energy of a particle of mass m moving in x direction. This actually comes from corresponding linear momentum operator square, which we will discuss later on. But in this way, we are able to define T cap, and therefore Schrodinger equation becomes minus h square divided by 8 pi square m d2 by dx2 psi equals E psi. So this is the Schrodinger equation of a particle of mass m moving along x direction and having potential energy equal 0. Now one may say that suppose the particle is moving not in one direction or one dimension but in a plane, and suppose that plane is defined by two dimensions x and y. In that case, as you can see here, kinetic energy operator T would be having two values. One will be the contribution coming from x direction, and secondly it would be from y direction. So it becomes minus h square upon 8 pi square m del 2 by del x2 plus del 2 plus del y2 in parentheses. So this is the corresponding kinetic energy operator, and when it operates on psi, we get corresponding E psi. So this is the Schrodinger equation for a particle of mass m moving in xy plane. Similarly, by a similar argument, we can extend our discussion to the point that if a particle were moving in three-dimensional or in space, then the corresponding kinetic energy operator will be minus h square upon 8 pi square m del 2 by del x2 plus del 2 plus upon del y2 plus del 2 upon del z2. This whole thing in the parenthesis is called Laplacian operator, that is del squared. Therefore, in short, we can write down Schrodinger equation as minus h square upon 8 pi square m del squared psi is equal to E psi. So this is the Schrodinger equation for a particle of mass m moving in space and having potential energy equal to 0. So you see now that it's not difficult to write Schrodinger equation for a system, and that is always the first step in the operation of quantum mechanics. Now one may ask that had the potential energy been not 0, then if potential energy were not 0, then potential energy operator would be equal to potential energy of the system, and that term will come. And similarly, if we were dealing, instead of one particle, we were dealing with n particles moving in space, then each particle in space will have its own x, y, z coordinates, and therefore it will have its own Laplacian operator, and therefore in that case, in that general case, Schrodinger equation will become minus h square upon 8 pi square summation del I square upon mi, and this summation is over all the n particles plus potential energy operator, which will be equal to potential energy of the system, and this whole is equal to E psi. Let's now discuss how the Schrodinger equation will change if we are dealing with a linear harmonic oscillator. That means an oscillator which is oscillating along x direction and its oscillation is simple harmonic. In that case, potential energy would be, according to Hooke's law, if we take into account that, potential energy would be equal to half kx square, and the corresponding kinetic energy operator would be minus h square upon 8 pi square m d2 upon dx2, because oscillator is oscillating along x direction. Now using these two terms, the corresponding Schrodinger equation, as you can see, becomes minus h square upon 8 pi square m d2 by dx2 plus half kx square. This whole is the Hamiltonian operator. This operating on psi gives you E psi. So that becomes the Schrodinger equation, time independent Schrodinger equation for a linear harmonic oscillator moving along x direction. After having written the Schrodinger equation, now the second step is that we define what are the boundary conditions for the system. That means the system for which we are writing the Schrodinger equation, let us define what are the restrictions imposed on that. what are the boundaries within which it functions or within which it works. So those need to be defined. For example, for a particle in one-dimensional box, suppose the one-dimensional box is of length L, then in that case, the boundaries would be between x is equal to 0 to x is equal to L. So these will be the two extremes between which the particle would be moving. In the case of an oscillator, which is oscillating along x direction, the corresponding boundaries would be, as you can see here, between minus infinity to plus infinity. So these two become the boundary conditions. In the case of a chemical system, suppose we are talking about hydrogen atom. In the case of hydrogen atom, electron can be near the nucleus. That is one extreme possibility. That would be r is equal to 0, or it can be at infinite distance, which is r is equal to infinity. So the boundaries would be r is equal to 0 and r is equal to infinity. Now one may ask that what is the purpose of defining boundary conditions? The purpose of defining boundary conditions is very simple, because ultimately from the Schrodinger equation we will get the wave function psi, and psi will be acceptable only if it satisfies the boundary conditions of the system. So that is very, very important, that psi must be a well-behaved function. So that is the important requirement. After having explained two steps, the first was writing Schrodinger equation and second was defining boundary conditions, let's come to the third step. Third step is perhaps the most difficult step, and this step is that we need to solve Schrodinger equation in the light of the boundary conditions. And this is a very difficult step. There is no general formula for this. Therefore, in quantum mechanics, most of the time we are focusing on the solution of the Schrodinger equation. And once the Schrodinger equation is solved, from the solution of the Schrodinger equation, what do we get? We get two things. One is the psi, which is the wave function of the system, and second is E, which is the total energy of the system. So these are the two outcomes of the solution of the Schrodinger equation. Now coming to the last step. Once we have solved Schrodinger equation and we have got wave function and the total energy, ultimately, we need to find out the properties of the system which we are studying quantum mechanically. This information we can get out of psi. Once we have been able to solve the Schrodinger equation, we will get two important parameters. One is the wave function and second is the total energy of the system. But now question is, once we have got psi and E, how will we get the properties of the system? Because that's ultimately the purpose of quantum mechanical study. Now this can be done through psi. Actually, psi is the most important parameter, psi is the most important function in quantum mechanics, because it contains entire information about the system. Therefore, it is also called storehouse of information. Now, question is how to extract information out of psi, and that comes under our fourth and the last step. Information about the system out of psi can be obtained normally by two important rules. One is, first we will try eigenvalue equation. This we will study in detail, how using eigenvalue equation we can get the values of certain operators or certain properties. And secondly, if eigenvalue equation is not satisfied, then we will use mean value theorem. So that's basically the last step in operation of quantum mechanics. So now you have seen that operation of quantum mechanics is very simple. It revolves around four steps: writing Schrodinger equation, defining boundary conditions, solving Schrodinger equation, and extracting information out of psi. And the entire quantum mechanics revolves around these four steps. If you remember, we learned about how to write a Schrodinger equation. We studied in the context of a particle in box. We studied about harmonic oscillator, etc. But now the question comes, if we have to study chemical systems, how will we be able to write Schrodinger equation? And how many terms would be there in the Schrodinger equation? That means in the Hamiltonian. Suppose there is a chemical system which contains n nuclei and e electrons. Then it has been shown that the total number of terms in the Hamiltonian would be equal to n plus e into n plus e plus 1 divided by 2. This is the general formula. This will be the total number of terms in the Hamiltonian. Out of these terms, kinetic energy terms would be n plus e, and potential energy terms will be split into, there will be electron nuclear attraction terms, VEN. Those will be n multiplied by e, Ne. Then there will be nuclear repulsion terms, which will be VNN, n into n minus 1 upon 2. And then electron repulsion term, VEE, which would be equal to E into E minus 1 upon 2. So these taken together will be the total number of terms in the Hamiltonian of a chemical system. We will see these terms in the case of chemical systems later on, but this is the general formula which you should remember. And you can see here that as the number of nuclei and number of electrons increases, the corresponding number of terms in the Hamiltonian will also increase. You can see in the case of hydrogen atom, there is one electron and one nucleus, so there will be only 3 terms. 2 will be the kinetic energy terms of electron and nucleus, and third will be the electron nuclear attraction term. And similarly for other systems it is defined. In the case of carbon, you can see there will be 28 total terms. In the case of methane, which has 5 nuclei and 10 electrons, the total number of terms will be 120. So that means quantum mechanically, as the size of the chemical system increases, solution of the Schrodinger equation becomes a bigger and a bigger challenge. And that's why we use computers in the quantum mechanical study, because manually it will not be possible to handle such large number of equations. So in this module, we have studied about the 2 fundamental equations of Schrodinger's quantum mechanics. One is time dependent and other is time independent. Time dependent is used for non-conservative systems, whereas time independent equation is used for conservative systems. Then we said that we have also studied that if we have to study any system quantum mechanically, basically it involves 4 steps. First step is how to write the Schrodinger equation. Writing Schrodinger equation means defining Hamiltonian explicitly. So once the Schrodinger equation has been written, second step is defining the boundary conditions for the system. Boundary conditions means the restrictions on the system. And after that, the third step is solving the Schrodinger equation in the light of the boundary conditions. And solving Schrodinger equation means solving the equation to get psi and E. And last step is extracting information out of psi, which is also called the storehouse of information. So these are the 4 steps which help in the operation of the quantum mechanics. And we also learned how to write Schrodinger equation for a chemical system, and we found that as the system becomes larger and larger, equation becomes very, very large, and therefore we use computational methods for storage and for solution of such equations.